So hello everyone, this is lecture 7 for the classical physics, in which we done up to here. We introduced this term, that is effective potential, and I told you that here it is a sum of this angular kinetic energy and the potential energy. Because both terms are depending only R, that's why we combine them and converted it into the form which we already know, and we solved it, something like this, in the previous lectures. So today we will see how this works, this equation works. So I need your complete attention to understand this, otherwise it will be go over your head. See, now we will have equation something like this: half mr dot square plus v effective r equal to E. So this is our radial kinetic energy, and this is our effective potential R equal to E, from where this v effective is this. So we all need these two terms. Let's analyze the effective potential curve. So in the previous lectures, where we were discussing about the harmonic oscillator and all, we just plotted V here, but now we will plot the V effective here, because that's that kind of form we have here. Okay, so we will plot V effective with respect to this R. Okay, and we take it only positive because R going from 0 to infinity only, and it is not going negative, because we are discussing the circular motion and the electrical and all kind of motions. So there will be R will be 0 or infinity, it won't be negative. That's why we are discussing only these terms only here. Okay, so we took this kind of curve and we will analyze this kind of curve, then we will see what kind of trajectories we are having. Okay, and what kind of motion they have. So before that, let me told you this thing. Means we will consider all the cases, all the possible energies. Okay, so different kind of energies can be there, like in the negative portion, in the positive portion, here, anywhere. Okay, so we will discuss all the cases. So let's take first case, that is E is less than V naught. So E is less than V naught, this point. So any energy less than this point means we are having somewhere here. So what kind of motion particle will have? So the phase trajectory will look like this, means it will be unbound definitely, because there is only one turning point. So let's say energy is here, then at this point when particles go like this, so at this point this total energy of the particle is equal to the effective potential energy. Okay, so at this point the radial kinetic energy is 0. Now understand this thing. In the previous lectures when we were talking, there was only potential energy there, and when potential energy becomes equal to total energy, kinetic energy turn out to be 0. But here at this point only radial kinetic energy is 0, but we are still having this angular kinetic energy which is combined inside this V effective, because at this point total energy equal to V effective, and V effective had the angular kinetic energy. That's why we are still having the angular kinetic energy. At this point the R distance won't change, but the angular kinetic energy will give us the turning point. Okay, so still we are having the angular kinetic energy. So let's try to see this curve in a little bit detail. So like this, if particle is having motion like this, so if particle is somewhere here, so there will be a component which is always towards the center, and that component is radial component. So let's say this is radial component. So this and we have this velocity component, the net velocity. So it can be resolved in two components, this is radial component and the angular component v theta. Now let's say at this point this is our total energy, and at this point this is our radial component, and this is our resultant velocity here. So the perpendicular component will always be v theta, and vr will be this. So we are still having this component in this side. Now see, at this point v theta will be in this direction, and vr will be in this direction, because both should be perpendicular. Then we will see that the total velocity is equal to v theta here, and at this point that's why we having vr equal to 0, because v theta is equal to vr here. And when you go in this direction again, then you will see at all points now this VR, radial velocity, is in the opposite direction. Means here it was always towards the center, and in this region it will be always away the center, this of source. Okay, so remember this. That's why we call this point as turning point. Okay, and this is what happened here. Means particle will come like this, and at this point this V effective potential equal to total energy, and particle will turn out at this point because of this angular kinetic energy, and will go like this. Okay, so this will be our first case. Means for whole this region less than V naught, for whole this case we will having this kind of motion. Okay, so put particle anywhere, it will go through the unbound motion, and this unbound motion can be hyperbolic or parabolic. Okay, so let's see some definitions. So at this point E less than V naught, V effective will be E. When V effective becomes E, then half mr dot square, that is radial component of kinetic energy, will become 0, and that's why we say that r dot becomes 0, that is Vr. Okay, so in this case motion of the particle will be unbound, as particle can move in a plane only under the influence of central force. So in planar motion only 4 type of conics are possible. So we already proved that particle can move only in a plane under the central force. So planar motion only can have the 4 types of conics are possible. So what are conics? Conics, you know, you study in the 10th maths. So you can have the different kind of paths when you pass a plane through a cone which is upside down, and you will have the elliptical, circular, parabolic and hyperbolic type of paths when you pass the plane at the different angles in the cone. So that's why we call that conics. So only 4 type of conics are possible, that are elliptical, circular, parabolic and hyperbolic. These 2 are bound and these 2 are unbound. You already know this. So here it will be unbound motion, so any of the 2 can be possible. We will differentiate later when we get this expression for the VR. Okay, only then we can say it will be hyperbolic or parabolic, but it is definite that it will be unbound here in this region. Now out of these 4 elliptical and circular orbits, out of these 4, these 2 orbits represent bound motion and bound motion, and parabolic and hyperbolic orbits represent unbound motion. So in the present case, nature of the orbit may be parabolic or hyperbolic. So I already told you this. Now there is this second case, that is when energy is at this point. We call it V naught. Okay, so at this point there will be 2 cases. One case is after this point, and one case is at this point, and the region between these 2 points is classically forbidden region. And why it is classically forbidden, let me tell you. Means, you know, the total energy is equal to sum of these, so kinetic energy can be given in this expression as E minus V effective. Now this is the curve of V effective. If energy is here, then at all these points this V effective is greater than E, so this whole term will came out to be negative. This whole term will came out to be negative in this region, so which is not possible because this kinetic energy can't be negative. M is positive and R dot will always positive because of square, so this term will be positive always. So that's why this region will be forbidden. So particle can exist at this point or at this point. So after this point it will be a unbound motion. I already told you what kind of motion is possible. If R is greater than or equal to A, then motion of the particle will be unbound and orbits may be parabolic or hyperbolic. But what happens when at this point? So at this point, you know, it will be E will be equal to V effective. So again this radial component will be 0, and we will see radial component will be 0, but V effective will be equal to V naught. Okay, total energy will be equal to this, and we will see that there will be kinetic energy due to this angular motion, because at this point V effective equal to total energy, kinetic energy along the radial component is 0. So and that V effective contains the angular kinetic energy term. So at this point only the kinetic energy of the particle is possible, which is of angular. Okay, so this energy is possible. So kinetic energy due to angular motion. So particle can undergo angular motion only at this point. Okay, in the cases we discussed earlier, there was potential energy only, so it was equal to total energy, so that's why there was no kinetic energy, so particle was resting at that point. But here V effective equal to total energy, and V effective contains the angular kinetic energy, that's why particle can go under angular motion here. And its radial component should be 0, means radial velocity should be 0 and it can go angular motion. So what kind of motion you can guess? It will be circular, because in circular motion you can see this radial velocity is 0, because particle, this radius is not going to change, that's why r dot will be 0 and r dot is velocity, and you will always have this v theta, okay, in the whole motion, because it is a 90 degree, that's why Vr equal to 0. So at this point the motion of the particle will be circular. So particle can go under angular motion. So there is one possibility for particle. In circular motion, radial velocity Vr is always 0, only tangential velocity is present, and that tangential is v theta. So you can see that at r equal to r naught, at this point it will remain same, so r dot will be 0, so that's why Vr is 0 and v theta is r theta dot. So v theta, you know, v is equal to r omega, and omega is theta dot. Okay, so now let's see some other things. So there is one more way by which we can prove that this motion will be circular. Let's see. At this point this del v effective divided by del r will be 0, because slope is 0 for this line. Definitely, you know, from this graph you can see that slope will be 0. So let's put it that way. So at r equal to r naught, this del v effective divided by del r is equal to 0. And what is v effective? V effective is this L square by 2m r square plus Vr equal to 0. Now let's differentiate. We will get minus L square divided by mr cube plus del V over del R at r equal to r naught equal to 0. Now take this to this side, so we'll get this del V over del R equal to r naught will be equal to this. And we substituted r naught in place of r, because it will be 0 at r naught only. Okay, we have find the points, it will be r naught, means this slope will be 0 at r naught only, that's why we have put it r naught there. I'm explaining again so that you don't have any doubt, so please understand this. So this is equal to this. Now what is this term? I already proved that this is force, central force. So Fr equal to this minus, you know what is L? L is m r naught square theta dot whole square divided by m r naught cube. Now after squaring all the terms, you will get some will cancel out. You will get Fr equal to minus m r naught theta dot square. So here because of the 1D motion, means it can be either minus or plus, means the force direction, because it is central force. So this minus sign represent only the direction of the force that will be inside. Okay, so this is not something negative, it's just direction which is negative. Okay, so we know what is theta dot from here, it will be v theta divided by r, so we get this. Now Fr is nothing but minus m v theta square divided by r naught. So see, this is nothing but central force equation, centripetal force equation, mv square over r. Okay, and you see that this depends only on the r naught, and r naught is constant, so it will be circular, means r naught is not changing. If r naught is changing, then we will have something different path, because all the elliptical and bound motions have the centripetal force, that's why they are moving, but their radiuses keep on changing, major axis, minor axis and all. But if it is constant, from this equation we can see it is constant, so it will be circular definitely. This equation is representing centripetal force, so motion of the particle with fixed radius will be circular motion. So that's how we proved that the motion will be circular at the point of this equilibrium. Okay, now what will be the angular frequency? So we know from here del V over del R equal to this minus L square m r naught cube. From here substitute L again, we will get this form, and from here we can directly find this theta dot, because it will be theta dot square and other terms will be cancelled out and m r naught will be remaining, so it will go in the denominator, and then square root of whole this term will get theta dot, and this theta dot is omega naught, that is frequency. So frequency of the circular motion is nothing but del v over del r equal to r naught m r naught. So remember this formula, very important, and here it is v, not v effective, so it is v which is inside this combined term, this v, so we'll use this term as a in this formula. Okay, so that's how you can find the angular frequency at the circular motion. Okay, so this is the formula for angular frequency of circular motion. This circular orbit will be stable in nature, because means this orbit will be stable, very much stable. If you perturb this energy little bit, so it will go, means its orbit will go under oscillations, but it will come to the circular again. That's why we call it stable. So let's see this thing in detail. This circular orbit will be stable in nature because if we perturb this circular motion by providing some extra energy, very infinitesimally small energy, then particle will start oscillating in the radial direction about r equal to r naught, but particle will not leave its original circular orbit. So let's say particle is moving like this in the circular motion, and you perturb the energy, means particle was here and you perturb the energy, you give some delta E energy, so that delta E energy will totally go into the kinetic energy, radial kinetic energy. So you can see here, this was the energy at r equal to r naught, and this E was totally equal to V effective at this point. Okay, that's why this 1/2 mr dot square came out to be 0. But if we give some delta E energy to this, E plus delta E, then this E equal to V effective, this will cancel out, and this whole perturbed energy will go to the radial kinetic energy. Okay, so we will have some radial velocity. Now particle moving in this, so it can go into the radial motion also. So if particle is moving, it can go under radial motion, so it will go something like this, but it will still be in the circular motion, and with time it will back down to the circular motion, damp down. Okay, so it will retain the stable circular motion. That's why we call it stable. So let's see more in detail what kind of oscillations will we have and what will be the frequency of those oscillations. So see this curve, this is again the same curve. Now we give the delta E energy, and energy came out to be at this point. This is very small energy. Okay, so very small oscillations will be having. So if particle is here, then it will have some this radius r1 and r2. See, from this point you can see this r1 is small and this r2 is maximum, so it will go into the minimum and the maximum radius. Okay, so this will be the radial motion, means particle can go radially to the minimize to this distance and maximize to this distance. So that's why we can see this is actually r naught, this is r naught, this whole radius is r naught, and this small one is a and this big one is b. Okay, and this a is nothing but r1, and this big one is r2. Okay, so these points are a and b. Okay, so we can see that particle is moving. Now it can go to the maximum distance up to b, up to this point, and it can go minimum to the distance of this r naught, sorry, a. So this point is a, this point is b, it can go maximum to the b and it can go minimum to the a, but still it is going under the circular motion, so it will retain the circular motion while going to the oscillations. So just imagine this. If you are still having any doubt, put it in the comment section, I will try to resolve. Now we will find the frequency of this oscillation, means this particle is oscillating definitely and it is going under circular motion. So we will see what will be the frequency of this oscillation. So this will be same as we discussed in the previous lectures when we were discussing the stability analysis, and there we came to the place for the small oscillations and we find the expression for the frequency, that was this del square v over del r square, but here it is v effective, so we will get the del square v effective divided by del r square at r equal to r naught divided by m. So this will be our expression for the frequency of this oscillation. Remember this formula, very important. So how you can prove this is will be just the same as you proved that time. So it will be this, and you can expand this by the Taylor series, and then you will get this expression. So here just remember this expression, you don't need this proof. So we discussed up to here for the V naught. Now let's say particle is somewhere in between this energy and this energy. We call it as V naught 1 and this is V naught. So energy is between V naught and V naught 1. So what happened at this point? So let's say these will be the turning points. Okay. So what kind of path we will get? See, this will be the minimum distance and this will be the maximum distance, and it will have always have the means only at these 2 points the radial component will be 0. I already told you why it will be 0, but at these points it will having the angular component of the kinetic energy. So that's why these turning points will give the angle, and there will be no radial motion at these 2 points. So what kind of trajectory we will get? We will get the elliptical trajectory. So when E3 equal to V effective, so at these turning points, this total energy will be E3 will be equal to V effective, and half mr dot square will be 0. So at turning points radial kinetic energy is 0. In between turning points radial kinetic energy can be non-zero. So in between here the radial kinetic energy can be non-zero, but at these points it will be 0. So between C and D points, when R is between C and D points, it can be non-zero. So how can we prove that? We know from the expression this half mr dot square equal to E minus V effective. Now in this reason we see that this total energy is greater than this V effective, so the difference will be positive always. So that's why between this we will have this radial component, but only at this turning points radial component will be 0. So let's see. Particle will undergo bound motion with r max and r min as maximum and minimum radius during the motion of the particle. This type of bound motion is represented by elliptical orbit. So from here we can see when particle will be here, it will be a minimum distance turning point, and here it will be a maximum distance turning point. So when you have different distances, minimum and the maximum distance for the turning points, you will have this elliptical type of orbit. So how? Because here you have 2 foci, and at each focus you will have this minimum distance and the maximum distance, and at both these points the VR is 0. So because this is perpendicular, totally perpendicular, and total velocity is also in this direction, so there will be only V theta and VR will be 0. Same here, VR will be 0. But meanwhile this path, anywhere if we take this point, then we will see that this is our total velocity, this is our radial component, and this is our theta component. So we will have both the components. Same it is if total velocity is in this direction, so we'll have this radial component always towards the center, and towards or away from the center radial component, and theta will be in this direction. So you can see this. So we will having these both components when it is between this region. But when it came to this point, we will see that this V will become parallel to the V theta, and this V will be equal to V theta only, and VR will be 0 here. There will be no perpendicular component here, and same here. And we can see that up to this region this VR is radially outward, but after this point it will be radially inward. So that's why we are calling these points as turning points, and these turning points are this and this, C and D. So I hope this is clear to you. We call this distance as R min and this distance as R max. Okay. Now if we place the particle at R greater than E, so it can be either here or it can be either this side. So if you place the particle after this E point, you can take this E point here, so it will be E point here. So after this point it will be unbound motion, as I already told you, and this middle region will be classically forbidden. So if we place the particle at r greater than e, then it will undergo unbound motion and possible orbits will be parabolic or hyperbolic. So same as always. Now there is case 4, that is E is equal to this point, means now energy equal to this V naught 1. So what happened at this point? So it will be the same case as here. At this point you can see that total energy is equal to V effective, no radial component, only the angular component. So an angular component contains the angular kinetic energy, so that will give the circular motion, because no radial motion, radial velocity is not there, so radial component will not be changing. And when radius is not changing, so that is possible only in the circle. That's why at this energy we will having the angular motion and it will be circular at this point. Okay, so when energy is equal to VO1, then we will have the circular motion, and it will be unstable circular motion, because if you perturb this energy, then it will go somewhere here and it will be unbound motion and it will go out of circle for forever. So at E equal to V naught 1, slope will be 0 again at this point. So del effective by del R at R naught 1 will be 0. So force will came out again this kind of form, minus mv theta square by R naught 1. So this is centripetal force. So orbit will be circular with radius equal to R naught 1, and motion will be bound motion. By perturbing this orbit will change into unbound orbit and they will move away from the circular motion. Due to this reason, this orbit will be unstable circular orbit. So I already described this. And the angular frequency of this circular orbit will be same as here. So it was del V over del R at R equal to R naught divided by mr naught 1. Okay, so you can use the same formula for here also. And at both these points for the circular region, del V effective divided by del R will be 0. Remember these formulas, we will use them in the questions, very important. So if we talk about the both circular motions, the stable circular orbit and the unstable circular orbit, for the stable one, angular frequency can be found by this expression, and here also angular frequency can be found the same expression. Here second order derivative will be greater than 0 because it will be minima there, and here it will be less than 0 because it is maxima there. So for maxima this should be less than 0, for minima it will be greater than 0. In a stable circular orbit, one can perturb the orbit and find the frequency. When it is perturbed, it will go something like this, and you can find that frequency by using this formula: del square V effective divided by del R square, R equal to R naught divided by m. But here perturbation, oscillatory behavior is lost. When you perturb this energy at the unstable point, it will go under the unbound motion and the oscillatory behavior is lost. So remember these points, very important for both. Case 5 is E5 is greater than V naught 1, means energy is somewhere here above this point. So it will be only one turning point here. So if E5 is greater than V naught 1, then there will be one turning point, and corresponding to that point, unbound motion will take place. Orbit may be parabolic or hyperbolic in this case. So now in the next lecture we will see some examples related to all these concepts. Then it will be clear to you what kind of questions can be asked from these topics. Okay, so we'll see you in the next lecture. Thank you everyone.